Hello everyone! This video is entitled Orbital Hybridization. Hybridization is a crucial model that helps us understand the behavior of atoms and molecules. It describes the mixing of atomic orbitals to form new hybridized orbitals in molecules, resulting in different energies and shapes. This concept is essential to understanding the shapes and bonding of molecules. Hybridization is an expansion of VSEPR theory, as it allows us to predict the geometry of molecules and the types of chemical bonds they can form. In this video, I will explore the basics of orbital hybridization, including the types of hybrid orbitals, how they are formed, and their role in chemical bonding. If you have not yet watched my video on VSEPR theory, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started.
Before I touch on the topic of hybridization, it's important to first understand why hybrid orbitals are required for atoms to form bonds. When a bond is forming between two atoms, the valence electrons in the bonding atoms are energized from ground state to an excited state by the interaction of the negative and positive electric fields of both atoms. The positive charge of each nucleus attracts the other atom's electrons. As these electrons move closer due to attraction, they encounter electron repulsion, which forces them to change positions to achieve stable orientations. Due to this excitation, electrons will transition into positions between the valence level orbitals, into a hybrid energy state. It is this occurrence that enables an atom to form more bonds to become stable. Let's examine carbon to further understand this concept. Carbon is oftentimes used as a model for hybridization because it's so widely used as the central atom in the formation of molecules. As a single unbonded atom, carbon has 2 electrons in its 1s orbital, 2 electrons in its 2s orbital, and 2 electrons in its 2p orbitals. Because of its electron configuration, carbon should only be able to form 2 chemical bonds due to the 2 lone electrons in its 2p orbitals. But experimental evidence has shown that carbon forms 4 equivalent bonds when it's in a molecule. Well, for carbon to have 4 singly occupied orbitals available for bonding, the energies of the electrons in the 2s orbital needs to merge with the energies of the electrons in the 2p orbitals to create an orbital level between those 2 orbitals that has 4 electrons of equal energy. Consider the compound methane, CH4. It's shown here bonding to hydrogen with 4 equal bonds. But in a ground state carbon atom, 2 valence electrons are in an s orbital and 2 are in p orbitals. Since s and p orbitals have different shapes and energies, these orbitals should form chemical bonds that also have different shapes and energies. So how then does carbon form 4 equal bonds in molecules such as methane? Well, the only explanation is the existence of hybrid orbitals. A hybrid orbital is an orbital that forms from the combination of at least 2 different orbitals. And hybrid orbitals are formed in the bonding process called hybridization, which is the dynamic means through which orbitals merge. Hybrid orbitals have different energies, shapes, and orientations in space when compared to their parent orbitals, and are able to form stronger bonds by allowing for greater bonding overlap. This idea of greater bonding overlap will be further explored in the next slide. But this image here shows the difference between hybrid orbitals and their parent ground state orbitals. As you can see, the size and shape of these hybrid orbitals are the same, and they appear to be the product of the merging or blending of these ground state orbitals. Let's revisit our methane example. Shown here are the ground state electrons in the central carbon atom of methane in the ground state orbitals. Now, during hybridization, this 1 electron in the 2s orbital will jump into this empty p orbital, and that will create 4 half-filled orbitals, 3 p orbitals and 1 s orbital. These 4 orbitals will then merge together or hybridize to create 4 equivalent hybrid orbitals we call sp3. Now, the reason we call them sp3 is because you have an s orbital with 1 electron being added to 3 p orbitals with 3 electrons, giving you sp3. And especially now, we need to note that we have 4 sp3. So again, the merging of p3 with s1 gives you sp3, but we have 1, 2, 3, 4 of them. So we have 4 sp3 orbitals. They're exactly equivalent in size and energy. The only difference between them is that they have 4 different orientations in space, so that of course they don't overlap with each other. So to review, you have one s orbital with a single electron that will hybridize or merge with 3 p orbitals, each with an individual electron, to create 4 sp3 hybrid orbitals with this very distinct size and shape. Please note that this dumbbell shape is of one single p orbital, and so you'll have 3 of these shapes merging with this s orbital to create 4 of these hybrid orbitals. Now again, the notation sp3 comes from the fact that you have p orbitals that house a total of 3 electrons, and those will merge with one s orbital with a single electron, and so the 1 is dropped from the notation, leaving behind sp3. So this brings up the obvious questions. Why do we need hybrid orbitals? And why are hybrid orbitals used in some chemical bonds? Well, hybrid orbitals are required for certain chemical bonds to occur. Without them, the orbitals in certain atoms would not be able to overlap to create a bond. And so the orbitals in each atom hybridize to enable bonding. Let's take a look at this process in action. Here we have atom 1 and atom 2, which are about to approach each other to create a bond. Before they approach each other, they've already hybridized to create sp3 orbitals in each atom. Atom 1 has its sp3 orbital with a positive spin electron, and atom 2 has an sp3 orbital with a negative spin electron. It's important that they have opposite spins so that they can come together and occupy the same orbital space. When they come together, the 2 hybrid orbitals overlap to create this bubble of space for a bond. This space allows for the 2 opposite spin electrons. Now, note the dotted lines. These dotted lines represent where the nuclei of atom 1 and atom 2 are. And so the nucleus of atom 1 is this dotted line, and the nucleus of atom 2 is the second dotted line here. Now, if we were to have 2 original p orbitals in atom 1 and atom 2 come together to create a bond, you would see that both of these orbitals do not reach each other to create this overlap. You can see that the nucleus of atom 1 and atom 2 are exactly in the same spot, but the p orbitals do not overlap to create a bonded orbital. And so hybrid orbitals are required for this greater overlap for the bond to even occur. Shown here in 3-dimensional space is methane, CH4. Now, I'm going to overlap it with the X, Y, and Z axes so that I can show you side by side what its s and 3p orbitals would also look like in that same space. And so there's the s orbital, and here are the 3p orbitals. You'll notice that its original s and p orbitals do not coincide with the tetrahedral shape that this molecule has in 3-dimensional space. However, when you hybridize those orbitals, you create 4 sp3 orbitals that directly coincide with this tetrahedral shape. And so, of course, it brings to reason why this shape occurs. This slide is a great summary of what I've discussed so far. sp3 hybridization is a mode of hybridization where one s orbital merges with three p orbitals to produce four sp3 hybrid orbitals. My primary example has been methane, shown here. These hybrid orbitals have 25% s character and 75% p character due to the ratio of 3 to 1. Since the sp3 orbitals are primarily p in character, each of these orbitals has one large lobe and one small lobe pointing in the opposite direction. These hybrid orbitals are created so as to form single bonds. Each sp3 hybrid orbital is identical with an unpaired electron. In methane, each orbital overlaps with the 1s orbital of a hydrogen atom to form 4 equal covalent bonds. Now, in situations where you don't want to create 4 equal bonds, and you may want a double or a triple bond, different forms of hybridization may occur within the central atom. These orbitals orient themselves at 109.5 degrees, forming a tetrahedral shape. And so the large lobes of the sp3 orbitals have a tetrahedral arrangement, giving the methane molecule its tetrahedral structure. And so here we can see the formation of these 4 equivalent single covalent bonds. These hydrogens arrange themselves around these sp3 hybrid orbitals and then move inwards to overlap to create these bonds, allowing for methane to have this tetrahedral structure. This slide again shows the 4 ground state orbitals before hybridization and the 4 hybridized sp3 orbitals. Each one of them has a different orientation in space, and when put together, these 4 orbitals create a tetrahedral arrangement that provides molecules such as methane their VSPER structure. Now, although you know that there are 3 different categories for bonding, single, double, and triple bonds, what you don't know is that these 3 categories actually fall under 2 distinct classifications: sigma bonds and pi bonds. Let's first focus on the sigma bond classification. Pi bonds will be covered later in this lecture. A sigma bond is a bond type that occurs when the 2 bonding orbitals of different atoms overlap between the atomic nuclei. It is formally defined as the overlap of orbitals along the bond axis of 2 atoms. And so the bond axis is an imaginary line between the 2 atomic nuclei. This image shows the overlap of 2 sp3 hybrid orbitals from 2 different atoms. Each red sphere represents the nucleus of each bonding atom. You can clearly see that the overlap is occurring between the 2 atomic nuclei. A sigma bond is created when any 2 orbitals overlap along this bond axis, represented by this dotted line. When this overlap occurs, it creates a very large sigma bond orbital, which again exists between the 2 atomic nuclei. And so, of course, it makes sense that the greatest electron density within a molecule is along the bond axis. Again, bear in mind that a sigma bond can occur between any type of orbital. It can occur between s orbitals, p orbitals, or hybrid orbitals, or a combination of the 3. Now, considering that each atom with an sp3 hybridization has 4 hybrid orbitals, each one of these sp3 hybrid orbitals will overlap with the atomic orbital of another atom to form 4 sigma bonds. Since each of these sigma bonds involves the sharing of 1 pair of electrons, these sigma bonds are considered to be single bonds. And so that's where the category comes into play. This slide shows examples of sigma bond formation. Here you can see that sigma bonds can be formed from the overlap of a variety of different types of orbitals. The first example is of two s orbitals overlapping with one another to create a hydrogen molecule. Here you can see the 1s orbitals of two different hydrogen atoms overlapping with one another to create one large sigma bond orbital, again with the electron density firmly held between the two atomic nuclei. The next example is of two p orbitals overlapping end-to-end to create the fluorine molecule. These two dumbbell-shaped orbitals must overlap end-to-end to create a sigma bond. Now, I must ensure that you take note of the fact that these p orbitals can only overlap end-to-end to create a sigma bond. I'm going to reiterate that. If these two p orbitals do not overlap end-to-end, it is not a sigma bond. They must overlap end-to-end to create a sigma bond, which forms this large sigma bond orbital, again with the electron density between the two fluorine atoms. The last example I have to show you is of the overlap between an s orbital and a p orbital to form the compound hydrogen fluoride. Here you can see that the s orbital from the hydrogen atom overlaps with the p orbital from the fluorine atom to create this one large sigma bond orbital. As I mentioned earlier, there are different forms of hybridization based on the bonding requirements of the central atom within a molecule. If the central atom needs to create only single bonds, then it will hybridize its valence electrons into sp3 orbitals. However, if that central atom needs to form one double bond alongside its single bonds, it must hybridize to create sp2 orbitals. sp2 hybridization is a mode of hybridization where one s orbital merges with two p orbitals to produce three sp2 hybrid orbitals. These hybrid orbitals have 33% s character and 67% p character. This is due to the ratio between the two p orbitals and the one s orbital. These hybrid orbitals are created to allow the central atom to form a double bond. These orbitals orientate themselves 120 degrees apart, forming a trigonal planar shape. Carbon is capable of forming double bonds due to this type of hybridization. Carbon hybridizes to allow for a bonding atom to get close enough to form a second type of orbital overlap. Let's take a look at this type of hybridization within carbon. Shown here is carbon's valence electrons in ground state. Just like in sp3 hybridization, one electron in carbon's 2s orbital will jump to the empty p orbital to create 4 half-filled orbitals. But unlike in sp3 hybridization, in sp2 hybridization, this 1s orbital will hybridize with only 2 p orbitals to create 3 sp2 hybrid orbitals, leaving behind one intact p orbital. Again, the notation sp2 comes from the fact that we have 2 p orbitals hybridizing with one s orbital to create 3 sp2 hybrid orbitals. This image shows the orientation of these 4 orbitals, the 3 hybrid orbitals and the 1 p orbital. In blue, you can see the 3 sp2 hybrid orbitals, orientated 120 degrees apart, creating this trigonal planar shape. The 1p orbital is left intact and is vertical exactly 90 degrees away from the 3 sp2 hybrid orbitals. This slide will show a more in-depth look at the result of this type of orbital hybridization. Formed are three sp2 hybrid orbitals from the merging of one s orbital with two p orbitals. On this three-dimensional grid, you can see the placement of the three sp2 hybrid orbitals. Left intact is one vertical p orbital in the center of this orbital hybridization. This p orbital will be instrumental in the formation of a double bond. It is used to create a second type of orbital overlap with another bonded atom. Here you can see the three ground state orbitals before hybridization and the three sp2 hybrid orbitals after hybridization. These three hybrid orbitals have different orientations in space, and when placed together, create this trigonal planar arrangement. So the question that needs to be answered is, why would a p orbital be left intact when an atom undergoes sp2 hybridization? Well, the answer to that question is pi bonds, the second bond type classification. Sigma bonds do not explain the sharing of multiple electrons, which are required to form double or triple bonds. In a double or triple bond, the p orbitals of two different atoms are oriented parallel to one another and overlap side by side to form a pi bond. This image here shows the p orbitals of two separate atoms that overlap side by side to create pi bond orbitals above and below the bond axis. Now, it's incredibly important to note that this type of overlap only occurs after two atoms have already shared a pair of electrons together through the use of a sigma bond that is along the bond axis between the two atomic nuclei. This type of bond is only used to facilitate the sharing of an additional pair of electrons between two atoms, and so it is through the use of pi bonds that atoms are capable of forming double or triple bonds with each other. It is crucial that you understand that these p orbitals overlap side by side so that the electrons that are shared will hover either above or below the bond axis. This is due to the fact that there already exists a shared pair of electrons along the bond axis because of the sigma bond that was first created between the two atoms before the double bond was attempted. This type of side-by-side overlap ensures that the second pair of electrons that is being shared by the two atoms does not occupy the same space. And so remember, the two electrons that were already shared in the sigma bond are occupying the space between the two atomic nuclei along the bond axis. And so a side-to-side overlap allows for the electrons to either be above or below the bond axis so as not to occupy the same space as those two shared electrons in the sigma bond. So to review, let's say two atoms with sp2 hybridization come together. A sp2 hybrid orbital from each atom will overlap along the bond axis to create a sigma bond. This allows the sharing of the first pair of electrons. Now, there is a single bond between those two atoms, but the two atoms want to share a second pair of electrons between them to create a double bond. So they will use the p orbitals left behind by their sp2 hybridization to form a second type of orbital overlap that will allow the sharing of a second pair of electrons. These electrons will be shared away from the bond axis where the first pair of electrons are already being shared in a sigma bond. What confuses students is the existence of two pi bond orbitals, one above and one below the bond axis. It's important to note that the shared pair of electrons in a pi bond will exist in only one of those bond orbitals. So it cannot exist in both. The pair of electrons that's being shared, the second pair of electrons that's being shared, cannot exist in both of these orbitals. It will only exist in one of these two orbitals. Because of the probability distribution of the two electrons being shared, it's impossible to know if the electrons will be above the bond axis or below the bond axis after the p orbitals overlap side by side with each other. Because of this, scientists have stated that there are two possible locations where you can find the shared pair of electrons. They will either be above the bond axis or below the bond axis, but never in both. An example of pi bond formation can be seen in the molecule ethene, C2H4. Ethene is a hydrocarbon with a carbon-carbon double bond. In order for the carbon atoms in ethene to create a double bond, they must hybridize. The type of hybridization these two central carbon atoms undergo is sp2 hybridization. You can see that because of the sp2 hybridization, each central carbon atom is surrounded by 3 hybrid orbitals. These hybrid sp2 orbitals are creating sigma bonds with 2 hydrogen and 1 sigma bond along the bond axis with the adjacent carbon atom. And so a sp2 hybrid orbital from each carbon atom overlaps along the bond axis to create a sigma bond. And so this is the first of the 2 bonds that will be created between the 2 carbon atoms. The p orbitals that were left behind by this type of hybridization overlap side by side to form the pi bond between the 2 carbon atoms. And so this essentially accomplishes the second of the 2 bonds between the 2 carbon atoms. So therefore, a double bond consists of 1 sigma bond and 1 pi bond. The first of the 2 bonds is the sigma bond between the 2 carbon atoms, and the second of the 2 bonds is the pi bond. Now remember that a pi bond has the sharing of 1 pair of electrons that will either exist in the pi bond orbital above the bond axis or below. It's because of the probability distribution of the electrons that we are unsure where the electrons will be. We don't know if they're going to be above the bond axis or below. That is why we represent both of these orbitals in this drawing. However, the electrons will only occupy one of these 2 pi bond orbitals, not both. And so in a double bond, you only have the sharing of 2 pairs of electrons. 1 pair between the 2 carbon atoms, and 1 pair either above those 2 carbon atoms or below those 2 carbon atoms, not both. So a pi bond forms alongside the formation of a sigma bond, providing the double bond between 2 atoms. So let's visualize the bonding between the 2 carbons in ethene step by step. First, the 2 atoms line up side by side, and they approach one another to form their sigma bond. The 2 central sp2 hybrid orbitals then merge to create one large sigma bond orbital. Now that the 2 carbon atoms have a single bond between them, it is now time to form the double bond, which occurs through the side-by-side overlap of the 2 p orbitals that were left intact by the sp2 hybridization. The side-by-side overlap of the 2 p orbitals have created 2 pi bond orbitals, one above and one below the bond axis. This is imperative to ensure that the electrons being shared between the 2 p orbitals does not exist within the same space as the electrons that have already been shared between the 2 carbon atoms within the sigma bond along the bond axis. With the placement of these electrons, you can clearly see that only 2 pairs of electrons are being shared between these 2 carbon atoms. 1 pair is between the 2 atomic nuclei along the bond axis within a sigma bond, and 2 occur within one of the 2 pi bond orbitals. Now, I placed them in the bottom orbital but that is arbitrary. I could have very easily placed them in the orbital above. All that needs to be known is that these electrons can only exist in one of these two pi bond orbitals. With the overlay of the structural diagram, you can clearly see that these bonds must occur the way that they do to form the double bond. The two purple orbitals are the pi bond, and the one large blue orbital in the center is the sigma bond. Having more than one bond between the two carbon atoms in this compound, of course, makes this compound stronger than it would be if it only had one bond. However, the strength of the compound has nothing to do with its reactivity. In fact, this compound is more reactive than it would be if it only had one bond, and this is due to the larger amount of electron density between the two central carbon atoms. Pi bonds are weaker than sigma bonds because their electron density is further away from the positive charge of the two bonding nuclei. If an atom wanted to bond to this compound, it need only come in from the top and grab this pair of unsecured electrons that are not properly held by the positive charge of the two atomic nuclei. Unlike the electrons in the sigma bond that are firmly held by the positive charge of the two bonding atomic nuclei, the pair of electrons that are either above or below the bond axis created by this pi bond are easily grasped by any reactive species that comes in to form a bond with this compound. Hence why molecules with carbon-carbon double bonds are more reactive than those with only single bonds. Now, this is not to say that a reactive element will come in and break both bonds. No. What's being said here is that the pi bonds, or the electrons that are being held in that pi bond, are much easily accessible to any reactive element. So if an element were to come in, it would break the pi bond first, and it would require a second element to come in to break the sigma bond. However, it would require a lot more energy for that second element to break the sigma bond because it's a much stronger bond being held by the positive charge of the two atomic nuclei. Now that we've discussed the hybridization required for single bonds and double bonds, let's discuss the hybridization required for triple bonds, which brings us to sp hybridization. This is a mode of hybridization where one s orbital merges with one p orbital to produce two sp hybrid orbitals. These hybrid orbitals have 50% s character and 50% p character due to the 1-to-1 ratio between the s and p orbital. These hybrid orbitals are created to allow the central atom to form triple bonds. These orbitals orientate themselves 180 degrees apart, forming a linear shape. Let's take a look at how carbon hybridizes to create sp orbitals. Shown here are the ground state valence electrons of carbon. As always, one of the electrons in the 2s orbital will jump into the empty p orbital to create 4 half-filled orbitals. For sp hybridization, this s orbital will hybridize with one p orbital to create 2 sp hybrid orbitals, leaving intact 2 p orbitals. This image shows these orbitals oriented around the central carbon atom. Represented in blue are the 2 hybrid orbitals protruding in opposite direction of the central carbon atom. And in yellow, you have the 2 p orbitals, one vertical p orbital and one horizontal p orbital. For the compound ethyne, C2H2, represented here, you have 2 carbon atoms that form a triple bond. This is made possible because of the 2 intact p orbitals. The vertical p orbital will of course create a pi bond with a side-to-side overlap as it did in sp2 hybridization. This horizontal p orbital will allow for a second side-to-side overlap, but this time along the x-axis. And so we will have one pi bond and a second pi bond, contributing 2 more bonds to the pre-existing sigma bond that always forms between the 2 carbon atoms. And of course, that's facilitated by this hybrid orbital here. And so this hybrid orbital will overlap with the hybrid orbital of another carbon to create a sigma bond. And this vertical p orbital will do a side-to-side overlap, which creates 1 pi bond. And then this horizontal p orbital will do another side-to-side overlap, which will create a second pi bond. And so a triple bond is essentially 2 pi bonds and 1 sigma bond. Now, each carbon atom will be left with one other hybrid orbital, and that hybrid orbital will be used to bond with the hydrogen on either side of the molecule. This slide provides a more in-depth look at the result of this type of orbital hybridization. On this three-dimensional grid, you can see the placement of the 2 sp hybrid orbitals. Left intact are 2 p orbitals, one vertical and one horizontal, that will be involved in the formation of the 2 pi bonds required to create a triple bond. This image shows the ground state orbitals before hybridization and the sp hybrid orbitals after hybridization. You can see by their orientation in space that when they're put together, they provide the linear arrangement for the molecule. The example we've been focusing on is ethine, C2H2. Now, because of the orientation of these sp hybrid orbitals around the central carbon atom, one sp hybrid orbital is used by each central carbon atom to form a sigma bond between the 2 atomic nuclei. This will form the first of the 3 bonds required to create the triple bond in this molecule. The other sp hybrid orbital is protruding in the opposite direction and is used to form a sigma bond with a hydrogen atom, and this occurs on either side of the molecule. Next, you can see the formation of the pi bonds with the 2 p orbitals in each carbon atom. Each carbon atom is left with 2 intact p orbitals, one vertical and one horizontal. The vertical p orbital will do a side-to-side overlap with the vertical p orbital in an adjacent carbon to create the first pi bond. The horizontal p orbital in the first carbon will do a side-to-side overlap in the adjacent carbon with its horizontal p orbital, and that will create the second pi bond. And so here are the 2 pi bonds put together with the sigma bond in the center that will give you your 3 bonds for this triple bond arrangement. This image shows all of the bond orbitals formed as a result of these overlaps. The 2 bond orbitals with the hydrogen atoms on either side of the molecule. You have the sigma bond orbital in the center between the 2 carbon atoms. And of course, each one of these pi bonds creates 2 pi bond orbitals. And so the vertical p orbitals will create this pi bond orbital on the top and on the bottom. And the horizontal p orbitals will create these orbitals on either side of this molecule. Now, please bear in mind that a pair of electrons will of course exist within the bond axis. And so this is going to hold 2 electrons. And you will have a pair of electrons either above or below that bond axis, or in front or behind the bond axis. You will not have a pair of electrons in either one of these orbitals, only in 2 of the 4. Here I will take you step by step through the formation of a triple bond between 2 central carbon atoms in an ethine molecule. First, the 2 carbon atoms need to line up so that the sp hybrid orbitals are oriented in front of one another so that when they approach each other, they can overlap to create a sigma bond. Now that the sp hybrid orbitals have overlapped, they create one large sigma bond orbital in the center of the molecule between the 2 carbon atoms, and they create sigma bond orbitals on either end, forming a connection to the 2 hydrogen atoms. Now it's time to form the first pi bond. This pi bond will form through the side-by-side overlap of the two horizontal p orbitals in both carbon atoms. When they overlap, they create pi bond orbitals in front and behind the bond axis. The next pi bond will be created by the side-by-side overlap of the two vertical p orbitals in both carbon atoms. This side-by-side overlap creates a pi bond orbital above and below the bond axis between the two carbon atoms. When we overlay the electrons, you can see that there is a pair of electrons in every one of the sigma bond orbitals, and there is a pair of electrons for every pair of pi bond orbitals. And so the pi bond orbitals above and below can house one pair of electrons either above or below the bond axis. I've arbitrarily picked to place the electrons above the bond axis. And in the pi bond that forms pi bond orbitals in front and behind the bond axis, I've placed electrons in front of the bond axis. Again, it can be in either one of those two pi bond orbitals, but I've placed them in the pi bond orbital in the front. So to review, with every type of hybridization that we just discussed, we initially started off with a 2s orbital and 2p orbitals. Now, for sp3 hybridization, we created a geometric structure that is tetrahedral, and the example we covered was methane. For the sp2 hybridization, we created a geometric structure that was trigonal planar, and the example we covered was ethene. And for sp hybridization, the geometric structure we created was linear, and the example we covered was ethyne. Here are a number of examples with a variety of different elements as central atoms. We of course focused on carbon as the central atom, but we know for a fact that other elements can also undergo these types of hybridizations. For example, here is boron with an sp2 hybridization, and here is nitrogen with an sp3 hybridization. Now, you might be wondering, how do I identify very quickly the hybridization on a central atom that is not carbon? Well, it's as easy as knowing the geometrical arrangement of the electron groups around the central atom. And so for boron, you can see that boron has a trigonal planar arrangement of electron groups around its central atom. And so that, of course, must be the sp2 hybridization. Whereas nitrogen has a geometrical arrangement of electron groups that is tetrahedral, which leads us to believe that it is sp3 in hybridization. It also helps to know the types of bonds that are being formed on the central atom. And so sulfur dioxide, we know that sulfur is forming a double bond with oxygen. And it's only forming one double bond here, which means it needs one free p orbital to create that pi bond. The only hybridization that allows for that is sp2. Carbon dioxide, on the other hand, needs two free p orbitals to create two separate pi bonds on either side of the central atom. And the only type of hybridization that provides two p orbitals for two pi bonds is the sp hybridization. It also helps to know that the geometrical arrangement of electron groups around carbon is linear, which also leads us to believe that it has an sp hybridization. And with this slide, I conclude this lecture, and I hope you understood everything I discussed. Thank you for listening. All the best.